So thank you very much, Mr. Chairman, and thank you for the invitation to come here. I will now bridge a little bit with the field of Magnons, but the subject is not so much distinct from that what's going on before. I simply would like to show what in the field of Magnonics or Magnons Spintronics, the influence of all the spin-orbit coupling effects, spin-Hall effect, and so on, is. Why are we discussing this? Well, you all know, I mean, I have to advertise here Spintronics, the Magnons Spintronics. CMOS is coming to an end. You all know that. Novel paradigm is let's go back from particle computing, what you use in CMOS because we use particles. The electron, let's use waves, and then you can draft an entire family of logic devices simply using waves. And then the next question is, of course, what kind of waves would you like to use? And the answer I have for you is simply, instead of the charges, use waves, you use the Magnons, the quanta of the spin waves. And now we are already in media space, so what we can do. Why Magnon computing? Well, with Magnons, which are the quanta of the spin waves, the wavelength is very short, so scaling is not a problem. Frequencies can be very, very high, not yet very much explored, by the way. So a lot of research work to do. We have interference effects, which are easily accessible. We have nonlinear effects, which is very important for data processing, because somehow we need to manipulate the data. Everything can be done at room temperature. There is no Joule heat by the spin waves themselves, and that is why we talk sometimes in some communities even about insulatronics, because you can do it in heat. And if you do this kind of wave-based computing, you have a smaller footprint, you can do everything in the Magnon system, and what is very important, you have good converters to CMOS. So that is why we talk about Magnons Spintronics. And in my group, André Schumack is doing a lot of work on building logic devices from using spin waves. So just some logic devices here, a majority gate, a Magnon transistor. And if you would like to know more about that, that would be a separate talk. We talk about Magnons Spintronics sometimes, and the other time about Magnonics. So what is the connection? Well, it's very simple. Magnonics is simply everything we do with the Magnon. So building logic gates, data buffering, if you like. Magnon conduits are important, analog data processing. And then we have to interfere it to the CMOS world, because otherwise we wouldn't have any easy access. And this all together is then called Magnons Spintronics. What we have to do physically, especially for the future, and I show you a little bit in this direction, is we have to go into the deep exchange regime where the wavelengths are very small, where the frequencies can be very high, so the feature sizes are small. We have to develop efficient converters. We have to engineer the interactions. We have to look a lot into new materials. Again, that would be a separate talk. And of course, we can also do, I would like to advertise this here, macroscopic Magnon quantum state computing. That is my pet project for the moment, but no time again to do. What I would like to do in this talk is simply to focus now on efficient converters. And before I do so, let me simply mention my group. There is André Schumack, who does all the Magnon logics. There's also Philippe Perrault, who is actually here with a lot of connections here to Nancy. He spent his postdoc here. There's Vitaly Vazushka and Alexander Salda, who work very much on the Magnon classes and this kind of work. And we have a lot of external collaborators, just to name a few here. You see here all the names. So, well, one view graph about Magnons. I think that's the first talk on Magnonics. We have to solve the Landau-Lifshitz-Torque equation, which you are, I guess, all very aware of. The torque equation, and there is some damping term, because we always have dissipation to the outside world, outside of the Magnonics world. What we come up with at the end is waves. You see as such a wave characterized with a wave vector, wavelengths, and that is what we then can use. And the method we use, and I would like to point this out, is that what we developed in Kaiserslautern over all the years is 101 light scattering, inelastic scattering. Thank you very much. Okay. Yes. Is this okay? So scattering of light inelastically from the Magnons, so in second quantization language, the frequency and the wave vector of the scattered photon are changed just by the amount of the Magnons. This shows up in sidebands. And why is that important? Because we cannot only do a frequency analysis of the Magnons, we can also scan the laser focus across the sample, so we get spatial resolution. We can work with pulsed, excited Magnons, and then we can measure the time between excitation and detection, so we get the full temporal information. And we can change the light incidence on the sample. You see here these two characteristic angles, and doing so, we can vary the transfer to wave vector in this experiment. So we get the entire information about the Magnons. Now back to our field spintronic effects for Magnon converters. You know, we have 4 effects which are important here. One is spin bumping, so the processing moment generates a spin current in an adjacent material. We have the spin Hall effect, the inverse spin Hall effect. I'm not going to discuss it here because you have heard about it so much today already. And of course we have also the spin transfer talk, and I think Johan Ackermann will give you tomorrow morning right away. Where's Johan? Is he here? No, don't see. We'll tell you more about it, but you all know what spin transfer talk is. And we can use jointly the spin bumping effect and the inverse spin Hall effect to build a detector, because what happens is the spin bumping generates a spin current, and then the spin polarized electron current can be converted into a charge current, so we can electrically detect the Magnons. And I will show you now in the following that this works very, very well for dipolar modes, for exchange spin waves, as well as for propagating spin waves, and if you do it right, you even get additional information on top of it. So let's start with dipolar and exchange waves. A prototype experiment looks like that. You can do much more with this experiment. We use lithium ion garnet as a carrier for the Magnons on a gadolinium gallium garnet substrate, which is not of importance here. Then what we have is here a microwave line just to excite the Magnons. We also have some platinum stripe with some connectors, so we can measure the spin Hall effect, the inverse spin Hall effect voltage. And you see also the laser here focused, in this case from the back side onto the sample to do the polymer light scattering. The GGG substrate is transparent, so we can nicely do this experiment from the back side. We can apply a field, and we can vary the field, and then it works very nice. The heat field here is 2 micrometer thick in this example. So what happens? If we apply microwaves here, typically of the order of twice the frequencies of the Magnons we would like to see, then a process happens which is very, very much used in magnonics, that is parametric Magnon injection, parametric excitation. It simply means if you have a microwave photon sitting here, that this photon can decay into 2 Magnons, can excite 2 Magnons with opposite wave vectors here and there, so there is a dispersion frequency as a function of the wave vector, so we have a pair of Magnons, and then we simply have to look how do the dispersion of the Magnons look like. And you see here a couple of examples. You see the red mode, which is a surface mode. You see the blue mode, which is a backward volume mode. Just take it as many modes which can be excited, and then if we just have a frequency here which hits the dispersion curves at these points, we can excite the Magnons. Let me show you an example. For instance, what we can do, we can start with a reference scenario where just a microwave photon decays into 2 Magnons which are outside the dispersion curve you see here. Then obviously not much happens. If you do an experiment, platinum on YIT here, in this case, platinum for the inverse spin Hall effect, then we measure as a function of an applied microwave pulse to our system just the voltage. And why does it happen? Well, it's very trivial. This works like a microwave oven. You simply heat the platinum with the eddy currents, and the eddy currents generate a temperature gradient here. So the platinum is much warmer, much hotter than the YIG, and then the spin-Seebeck effect sets in, which always happens in these systems. And the spin-Seebeck effect creates here a current, and a spin current, and then this inverse spin Hall effect, we can detect the spin current as a charge current here. It's platinum, and that is what we measure here. An effect very common here in this field, so not very exciting. So what happens now if we excite the Magnons here? We do not only generate the eddy currents for heating the platinum layer, but we are now going into the field of magnonics. So basically what we now do is, let's excite some Magnons here, for instance. Here's this green curve. So then what happens is we excite the Magnons here, and then the Magnons, of course, shows a spin pumping effect. So we create an additional current here, spin current from the YIG, in the opposite direction to the one we have seen before from the spin-Seebeck effect, into the platinum. And if we do the measurement, we measure just this kind of curves as a voltage, as a function of the time when we apply the microwave pulse between here and there. And what we have to do, of course, we still have the heating, the microwave oven effect. We still have the heating, so we have to do the subtraction of these two curves. And this is now the curve of from the Magnons, which show here the inverse spin Hall effect signal. So obviously it works very nicely. We can separate these two effects. And so we can, basically what we have here is Magnons, and we can detect the Magnons here electrically. We can do more. For instance, we can vary the field, here moving the field up and down. And if we go, for instance, to a field where we excite these green Magnons here, then we are deep in the exchange regime, and you still see here from the difference, or you can see it here, a nice signal from the exchange Magnon. Somewhat weaker than we have seen before, but the signal is clearly there. And what you can do, actually what we did in my lab is that to do the full experiment, just measure this voltage as a function of the magnetic field, and with the magnetic field we vary the frequency and according to the dispersion curve, the wave vector, and then we see characteristic curves like you see here. So here you see actually the wavelengths as a function of the magnetic field for you as a reference, so you see that the wavelengths here at this end becomes very, very small, so the exchange modes. So we see the exchange modes very nicely here. If we go to the dipolar regime, the signal here is much, much, much larger. And the reason behind is very trivial, because at the interfaces you always have some homogeneities, and if you excite the exchange mode, you excite them predominantly in the middle of the film, just where the volume is. And you have to keep in mind that the inverse spin Hall effect, you all know, is an interface effect, and in this case, the precession amplitude as the interface is smaller, that is why the amplitude is here reduced, you can see. If we do the same for the dipolar modes, then these dipolar modes are fully extended over the full thickness, and correspondingly we get a much larger signal here. There's all simple physics behind what we can understand here. Actually, there's a small peak due to 3 Magnon scattering, which enhances the effect, but I have no time to discuss this. Let's go to the next point, and that is detection. We have already seen here the spin bumping and the inverse spin Hall effect. And now the question is, how well does it work for propagating spin waves? And let me show you what we can do. We can use a spin wave source and then inverse spin Hall effect detector, which we can now separate in space. And here is such an experiment here in brown. Again, is the GIG scribe. So we have just a classic antenna, nothing else, and just a copper stripe or gold stripe to which we apply some microwave pulses. So microwave pulses generate some spin wave pulses. If you do it right with a field and so on, we can just create any kind of propagating spin waves. So with small backward volume modes, this here is a backward volume mode, by the way. And then we have a platinum stripe here. And now the platinum stripe for us is a very, very friendly detector, since we can operate in 2 different modes. Mode number 1 is simply we just rectify the signal, then we get a DC signal, and then we measure the inverse spin Hall effect signal. Or we don't rectify, then we get the spin Hall effect signal, or we rectify, then we just use the platinum stripe as a standard inductive antenna, but just an electric AC signal is generated, and then we use rectifier, sorry for the mixing here, rectifier, and then we get just a standard setup that we pick up a signal with the standard microwave technology. So just by switching between these 2 modes, the DC signal or the AC signal, we get those things. Okay, then let's do such an experiment. Here is now, we do time resolved measurements in this case. Here we measure the spin wave intensity. That we can do with Bellon light scattering, by the way, independently too. We apply a pulse, and then for this antenna we have to wait some time because of the finite group velocity. And once the spin wave pulse arrives here at the platinum antenna, then it just generates some intensity, what you see here. We can measure the inverse spin Hall effect signal, and if you compare these signals, you see it more or less looks the same. But if you look very carefully, there's a small difference because you see the signal, it's just somewhat, it seems to be delayed. If you look more closely, you find some intensity here in the inverse Hall effect signal, which you do not find in the inductive signal. And of course we can do the probe. The probe is simply just reversing the field, and then the inverse Hall effect signal just reverses sign, as you would expect for this effect. So something is happening here, and of course you can do it for all different kinds of fields. You just change the field, you see the field here, and then you see especially here that in this particular case, then you see a large signal in the inverse Hall effect signal, which you don't see here in the direct intensity signal. Question is what happens here, and what helps us is Böhmer light scattering. That is a picture of a propagating spin wave pulse. So the spin wave pulse, so this is here the left right, so this is brown field. So the spin wave pulse is propagating from the left to the right. But if you look very carefully in these pictures, you'll see some kind of unusual noise here, which is clearly above the thermal noise spectrum. And that is nothing else than just an indication of exchange modes. And if you remember from the preceding view graphs, we can see exchange modes in the inverse Hall effect signal, so that is a contribution you find here. So putting this all together, you get a lot of information out of these kind of measurements. Okay, next point is if we can we excite spin waves via the spin Hall effect and the spin transfer torque effect. And issues which are important is damping, so can we reduce the damping, which we always have indeed with the coupling to the total system. Heating is an important issue because we deposit energy because magnons have a finite lifetime. We also saw eddy current heating. We might have outer oscillations here in the system if we just have enough current density. So let's see what happens here in this system. And again, I will show you there's a wide richness in this particular scenarios. So let's first start with a damping reduction in a macroscopic harmonic system, reference system for all the people who do just this nanocontact excitation. We simply wanted to know, can the spin Hall effect jointly with the spin transfer torque effect only be used in microscopic systems to reduce the damping, or does it also work for macroscopic systems? What is the entire fundamental difference between the two systems? What in the physics is the same and what might be different? And there is a very nice method, because we were using parametric generation of Magnons already, you have seen it before. And that method can be so nicely be used to measure damping, because if you have already spin waves and if you apply the parametric pumping process, then you eject Magnons. So you can measure very, very sensitively how many Magnons do you need to inject in order to compensate the decay of a Magnon population due to the damping. We put it with these words. And here you see a typical picture what we can measure. For instance, what we can do, we just measure the pumping field. So first of all, the color code shows the intensity of the spin wave of the Magnons, and then we can measure here the pump. We can vary the pumping field, so the strength of the parametric pumping field as a function of the applied field. And you see you need to have a minimum pumping field shown here by the horizontal dashed line, which you need to compensate for the damping, because if you further increase the pumping field, you see the intensity goes to green, to yellow, finally to red, so the amplitude increases, so you increase the population. If you only apply a very small pumping field, let's say here, nothing really happens because that is much too small to compensate the intrinsic damping. You can also discuss the critical field at which this happens, but that is not so important. You see the geometry, so the film is extended. We use a microstrip line here for the pumping. We have some contacts here which we can use to apply the current for the spin Hall effect, spin transfer torque effect. Okay, and things you can do now, let's start with this basic picture here with the bottom pictures. We have seen this picture here before, this picture you have seen before. We can now apply positive, negative currents. If the current is positive, you see the threshold increases. If the current is negative, you see it decreases. We don't have outer oscillation yet. For that, we would further on need to reduce the current. But you all know what happens if you have an infinite film. If you try to put a current here through through the platinum layer, then eventually the film will of course melt, so you would never reach it. But what you can measure is the damping now, and you see it here for positive, negative magnetic field. This is only just to show you that the symmetry is right, and you'll see that the damping changes here linearly with the current. And what comes out is you can, of course, from this calculate or extrapolate to the critical current you need. And what you find is that in the system, the spin Hall effect, spin transfer torque effect in these macro structures have the same efficiency like it is known in the nanostructures. So why do nanostructures oscillate and this macro structures not? The reason is very simple. It has to do with the mode spectrum. You have to have a very discrete mode spectrum that all the energy goes in the fundamental modes. If you have a continuum of modes, then all these modes get scattered. You go into the nonlinear Magnon regime. It's just another word. So the multiple scattering effects play a role, and you are never able to put enough Magnons into a signal mode to overcome the threshold which you need for auto oscillations. So that is simply here given the answer. There's more on this tomorrow. Victor Lauer will report about this tomorrow morning. Okay, let's discuss heating, which we actually found some results which we found a little bit surprising. The point is simply to compensate completely the damping. We need to have large current densities, and of course we switch over to microstructures for the heat dissipation problem I was already mentioning. But the question is, what is actually heating up here your sample? So what is the primary heat source? And you can think about two different sources. One is just a dual heating by the charge currents, and the other is the heating by the relaxation of the excited spin waves, because each Magnon carries h bar omega energy quantum, and this goes, of course, locally to the system, into the phonons primarily, so it heats up the system. What I show you here, by the way, is just this kind of geometry. So we use, in this case, a Heusmann material, CMFS, with a platinum cover and the chromium underlayer. That is, this chromium platinum is very good in order to have a very large spin Hall effect acting here in the system. You see the parameters here. I do not want to go into the detail. I know we can draw the DC current here between these lines. The result, just to jump to the result, what you find here is in black the normalized Brunner light scattering signal. So we measure now the BLS intensity as a measure of the number or the density of the Magnons. And we do it as a function of the applied DC currents for negative currents and for positive currents. And what you also can measure if you do Brunner light scattering is, of course, the frequency. And the frequency tells us something about the saturation magnetization. And the saturation magnetization in turn is a very nice sensor for the temperature, because the saturation magnetization is temperature dependent. And it tells us something about the Magnon population in addition, because for higher Magnons, the saturation magnetization is also reduced. And what you see very nicely is that for negative currents, the BLS intensity goes up, and also the frequency is reduced. So, first of all, what you see is not a signature of a dependence on the square of the current density, so there is no strong Joule heating here in the system. The frequency shift would be due to nonlinear spin-wave interaction or to spin-wave heating, and now we need to find this out. And to find this out, what helps us always is to go into the time domain and see how the system develops. And here you see the full beauty, what is going on. Brunner light scattering intensity as a function of the time. And what is shown here is also on the right side here the critical, sorry, the frequency of the Magnons, the center frequency, which is a measure of the saturation magnetization. And what you see initially, the frequency shift is proportional to the spin wave intensity. That would be in agreement with a nonlinear frequency shift or spin wave heating. And if you would only measure up to this point, you would have a nice theory how this all works together. But if you measure a little bit longer in time, you see that this very simple relation, frequency shift proportional to the intensity. So nonlinear frequency shift does not work. It just separates, so it is not anymore proportional. So you have a different decay time scales for the spin wave frequencies and for the spin wave intensity. And the answer why that is, or whether you can do more, there's a more accurate experiment here, to simply measure the center frequency as a function of the TLS intensity by evaluating all these systems. And we do it for different current strengths, and you see the curves all lie onto each other. So for the same spin wave intensity, the heating is independent of the charge current, and this means the decay of the spin waves heat go to the photonic system. So, and you know the phonons have a much longer decay time, so they store, so to speak, the energy here in between before it finally goes to the lattice. So heating is due to the relaxation of spin waves, and this has a significant contribution to the total dissipation in the system. I might mention here we have done other experiments where we even use it to develop a heat conveyor by the Magnons. If you do everything right, you really can transport heat. And for instance, you can bring the heat to the very end of a Magnonic waveguide and heat the end simply by using Magnons. So this works, and it fits very nicely into these results. Finally, auto oscillations. Like you get if you use microscopic samples, and the system we use is just a disk, 1 micrometer in diameter. Zinc is platinum, the sample is from Caroline Ross. Field is applied, here you see it's electric contacts, and then we have a high current density here in between, and we just want to know what is now the dynamics here in the system. Again, what we can measure here at the same time is the saturation time. You see here the raw data, so we measure the Bourdon light scattering intensity as a function of time when we apply here a current pulse, and we can measure the characteristic increasing time here, shown here with the red fits. So we get the saturation time, which you see here on the left side, and on the right side we see the corresponding current. And what you see is that the saturation time until the dynamic equilibrium, so here the steady state is reached, this varies with the current strength, and it depends on the strength of the spin transfer torque, therefore, and the maximum spin wave intensity saturates with increasing DC voltage, so we have a strong nonlinearity here in the system. So, why is that? Well, again, we can look deeper into the system, and again, to cut a long story short, what always happens in the system, you can have different modes. For instance, you can have modes which are localized here in the inner part of the disk. You can have modes which are more localized here in the outer part of the disk. This has been analyzed here. What you see here is measured normalized Bourdon light scattering intensity at 2 different positions on the sample. The position is just shown here by the red circle, and this is here the disk diameter. So there is a scan here in the x direction, so just here along this direction. And then what we eventually find is that, of course, the frequencies are very different. And then what we can do, we can measure the dynamics for both of these points separated with Bourdon light scattering. So the blue, this is a blue curve and the black curve. So the black curve is here in the center, and the blue curve is just here. It's a boundary of the disk. And you see the dynamics is very different. So obviously this we have to take into account. There are separate nodes which cannot mix. So obviously the dynamics is very, very different, and different spin wave nodes can have auto oscillations simultaneously in the short pulse regime. If you wait for longer, of course, the nonlinear processes second. More details is in a poster which you can see is presented by Michael Schneider from my group. So that is just a summary. I wanted to show you just a wide field what